My talk will have a lot of introductory material because Moonshine is a subject you rarely hear about. But if there's new material in the talk, it's because of this paper that we just wrote that has even an additional M in the title, Mock Modular Mathieu Moonshine Modules. It appeared on the archive earlier this week. And my collaborators, Cheng, Dong, Duncan, Harrison, and Race are responsible for anything correct that I say. So the outline of the talk is the following. There will be an introduction where I give you the 80s and early 90s preview of what Moonshine was. I'll then switch to geometry and motivate revisiting this subject. I think starting in 2010, there have been very good reasons to think about the subject again. And I'll close by describing briefly some of the highlights of this paper. Okay, so any talk about Moonshine needs to begin with some recap of the story to date because it involves many moving parts, and a lot of the moving parts are unfamiliar to most physicists. So at the heart of the old story, there were two classes of different beautiful non-geometric, but enigmatic objects from mathematics. One is that at the end of the last century, mathematicians succeeded in classifying all the finite groups. There were 18 infinite families, and in addition to these infinite families, there were 26 sporadics, sort of oddballs that don't fit in one of the classification of the 18 infinite families. So here's a picture of the sporadics and how they embed into one another. The largest of these things is the monster, which will star in the first third of my talk. And later in the talk, we'll encounter the Conway group and some of these groups found by Mathieu in the 19th century. Okay. And so the lines indicate who's a subgroup of whom. So this is one class of interesting objects. A second class of interesting objects that you probably know more about, at least if you're a string theorist, is the modular functions and modular forms. So we commonly in string theory encounter objects that have a large diffeomorphism group that acts in some way on the moduli that parameterize their metrics. So for instance, here's a torus. You can make a torus by identifying points in the plane by two lattice vectors, basis lattice vectors, 1 and tau. Okay. And then tori that are related by an SL2Z action on tau are actually equivalent, but these SL2Z transformations give large diffeomorphisms of the torus. Now, in string theory, we often compute things like a partition function at one loop on the torus that tells us the string spectrum. Or maybe in theories that have S-duality, this tau could be a space-time field, and then S-duality invariant actions would need to have nice modular properties. Okay, but in any case, when we compute such an object, we expect the answer not to care about which frame we chose to view tau in. And so we should get a modular function or sometimes a modular form, meaning when we perform the SL2Z action, either f should come back to itself, or if it's a form of weight k, it should come back to itself up to a certain multiplier, depending on the precise SL2 transformation. So monstrous Moonshine originated in a setting where the same people were looking, I guess during different days of the week, at these objects and at these objects. Okay? And one of these people, John McKay, noticed the following thing. The monster was just being constructed. The dimensions of the lowest dimensional irreducible representations were, well, there's always a 1, the singlet. The next guy is 196,883 dimensional. It then goes up to 21,296,876, and the numbers get bigger and bigger. Okay. Now, taking a break from studying this, I guess visualizing this representation gives you a headache. John read a number theory paper. And in this number theory paper, the famous J function plays a role. The J function, he noticed, has a Q expansion. Q is e to the 2 pi I tau, so that builds in invariance under tau to tau plus 1. Anyway, J has a Q expansion that begins with a pole. There's a constant, which is a convention. You can shift the constant freely. And then there's 196,884Q, 21493,760Q squared, and so on and so forth. Now, while mathematicians are famously inept at arithmetic, John did notice that there was a coincidence here, right? 196,884 is 196,883 plus 1. And in fact, at the next number, if you add the dimensions of the first two non-trivial irreps of the monster and the singlet, you get the next number in the Q expansion of the J function. So this led him to think and discuss with Thomson the idea that maybe there's really a deep connection between the biggest of these groups, the monster, and maybe the most basic of the modular functions. So what are these? Well, let's suppose that there's a physical theory whose partition function is this J function. The powers of Q measure the energy. in some convention, these would be states at energy -1, 1, 2, and so forth. And the coefficients here tell you how many states there are at that given value of energy. Okay? Well, if there were such a physical theory whose partition function was J, and if it had monster symmetry, then that could explain why the J function is related somehow to representations of the monster, because at each energy eigenvalue, there would be monster representations. Okay, so we can decompose our vector space into the -1 piece, 1, 2, 3. I'm shifting away the constant. So at energy -1, we would just have the trivial rep. Then you'd have the 196,883 plus 1, and so on and so forth. Okay. And you could go ahead and decompose the higher v sub n's too. Now, if this is true, you get a prediction. Because if there's really an action of the monster group, then you can also compute series that are associated to characters of representations at each value of the energy. So instead of just the partition function, trace of q to the L0, that's supposed to give you J, you could compute trace of g times q to the L0, where g is some element of the monster acting on this vector space. Now, of course, this is just a class function, because if you conjugate g, you can move things around in the trace and get the same thing back. But the monster has 194 conjugacy classes, so this gives you 194 functions that can test your knowledge of how the monster is playing with this would-be vector space. Now, in general, because you've inserted g in the path integral in the trace along the time direction, you shouldn't expect to get a modular function under SL2Z. But life is still pretty good, because when you put different boundary conditions on the A and B cycles of the torus and then act with an SL2 element, well, you know how the boundary conditions get mixed up. And some subgroup of SL2Z will still preserve the trace GQ to the L0, and hence should still be, acting nicely on this function TG. So TG should be a modular function under some congruent subgroup of SL2Z, determined by the order of the group element. So checking these McKay-Thompson series gave much further confidence, because given the monster decomposition, these things did land in the right spaces of modular forms, that there was really a story here. And because I have so little time, I'll just tell you the final upshot of that story. Various heroic mathematicians with very little help from string theorists worked out this story. Frankel, Lepowski, Merman, Borchards eventually proved various things and got a Fields Medal for it. But the summary is the following. So we have here J. We would like it to be the partition function of a physical theory, and it is. The theory is the bosonic string on a 24-dimensional lattice. In fact, a unique 24-dimensional lattice, the Leech lattice, which characterizes the densest way of packing oranges in 24 dimensions. That's not quite true. It's a Z2 orbifold of the Leech lattice, and these mathematicians invented the concept of asymmetric orbifold before physicists. So the bosonic strings on this asymmetric orbifold, on the one hand, have J as their partition function, and on the other hand, actually, you can construct an action of the monster group on this Leech lattice orbifold. So this was an explanation of monstrous moonshine. The reason that J is related to the dims of reps of the monster is that there's a monster symmetry, and J is the partition function of the theory with monster symmetry. Okay, so that story is beautiful. You will not read about it in Polchinski's book. You will not read about it in Green, Schwartz, and Witten. The reason you will not read about it is because since about 1986, nobody has cared too much about the bosonic string in 2 dimensions. Okay, so although it's a beautiful story, it led to profound mathematics, it hasn't been central in the development of string theory. Now, around 2010, I think there's a hint that maybe things should change, because Gucci, Oguri, and Tachikawa revisited the story of a certain modular form associated with one of the central players in string duality, a Calabi-Yau space known as K3. So let me explain what they found. For any 2, 2 superconformal field theory, this would be the world sheet of a string with Calabi-Yau target manifold, there's a particular thing you can compute. Now, previously we were talking about the physical partition function. That contains a lot of information, and it's hard to compute for any curved target manifold. But in supersymmetric theories, like these theories with 2, 2 supersymmetry, there are more refined things that are supersymmetric indices that you can still compute. One such thing is the elliptic genus. And what that is it's a partition function, except on the right, you just insert trace -1 of the f right q to the L0 bar. Now, although string theorists are highly sophisticated people, I took it that some of you haven't studied Jacobi forms before. So here's the definition. A Jacobi form of level 0 and index m Here, index 1 would be associated with K3, index 2 with the Calabi-Yau fourfold, and so forth, is an object that transforms as follows under various kinds of symmetries. Under modular transformations, phi transforms, well, it's almost like a modular function, but it has this exponential that depends on the U1 grading quantum number. And under something called elliptic transformations, it also transforms by this kind of a exponential. Okay, this elliptic transformation, which may be less familiar to you than the modular group, is associated with the fact that n equals 2 theories have spectral flow that can take you between the NS and Ramon sector, and in general to values in between. That's related to the existence of space-time supersymmetry in Calabi-Yau compactification. So anyhow, there is some Jacobi form associated with K3. It was computed in 1989 by Iguchi, Oguri, Taormina, and Yang. I probably slaughtered the pronunciation of the names. And it was actually expanded in n equals 4 characters. Since n equals 4 is a symmetry of K3, not just n equals 2, that makes sense. So it was expanded in characters of the n equals 4 superconformal algebra by Oguri in his thesis in 1990. There's an expansion that looks like this. There's 20 times some short representations or BPS representations. And then there's an infinite series of long representations. The indices here are the conformal weight and the J3 under the SU2 of the n equals 4 algebra. The n equals 2 algebra has an SU2R symmetry. So characters are labeled by a conformal weight and an SU2 J3. Okay. So what Oguri found in his thesis is that the ANs are 90, 462, 1540, and so forth. What Iguchi, Oguri, and Tachikawa realized in 2010 is that 90 is 45 plus 45, 462 is 231 plus 231, and so on and so forth. And these are dimensions of irreducible representations of M24. And when I went to Caltech to give a talk about what I'm talking about now, Oguri sent me a copy of his thesis and said, please see equation 3.16 where this appears. I did not know how to divide these by 2. Regards, Hiroshi. So you see, in monstrous moonshine, the trick was to add 1. Now we're much more sophisticated, and you have to divide by 2. Okay, so now here's another math object definition slide. I said that these are dimensions of irreps of M24. Since M24 and 23 and 22 will appear in the rest of the talk, I'll tell you a little bit about what the group is. I don't have a really good feel for it. So this is a sporadic group of order given here. It's 244,823,040. If you look it up in Wikipedia, the first thing it says is automorphism group of the unique doubly even self-dual binary code of length 24 with no words of length 4, or extended binary Golay code. So then you scratch your head and talk to somebody smarter than you. They explain what this means. What it means is this. Consider a sequence of 24 zeros and ones. We're going to define a set G. Any length 24 word that we include in this set is a string of zeros and ones that has even overlap with all other such strings that we've said are in G. The number of ones in each element in G is divisible by 4, but not equal to 4. And then the subgroup of the permutation group on 24 objects that preserves this set is M24. M22 and M23 are subgroups of the permutations in M24 that stabilize either 1 or 2 further points. Okay, so these will be the heroes of the later part of my talk. Okay, so this M24 moonshine, the relation between the Jacobi form associated to K3, the elliptic genus, and these representations, and now a very large set of generalizations that associates a moonshine with each Niemeyer lattice. These are other preferred 24-dimensional lattices distinct from the Leech lattice called umbral moonshine. These moonshines have been investigated pretty intensely in the past few years. The full analog of this story of monstrous moonshine, where really there was a string theory and a partition function and a symmetry, is not yet clear. You'll hear about aspects of this story, I think, in Miranda's talk tomorrow. But in particular, with this M24 case, no K3 conformal field theory and no known precise auxiliary object associated with a K3 conformal field theory yet gives an M24 module with the desired properties. Okay, so the story is not yet at the level of perfection that the story with the monster was. Now, the starting point for the work I'm going to report was a desire to extend these kinds of results to Calabi-Yau manifolds of higher dimension. Of course, we'd also like to understand fully what's going on with K3. So the first step when you're extending from K3 is to go to Calabi-Yau threefolds. And we did this in the following cheap way that I talked about at strings last year. So K3 can be considered as a compactification manifold not only for type 2 strings, but also for heterotic strings. So there's a duality where you compactify heterotic strings on K3, well, times a torus to get to 4 dimensions. And that structure is dual to type 2 strings now on Calabi-Yau threefolds to get to 4 dimensions, with both sets of theories preserving n equals 2 supersymmetry. The details of the story aren't important for my talk. You have to put some instantons in the heterotic E8 times E8. Those map to some data characterizing a particular class of elliptically fibered Calabi-Yau threefolds in type 2. But the upshot is, because of the M24 found in the elliptic genus of K3, there's a related M24 structure appearing in the heterotic string, not in the elliptic genus, but in something called the new supersymmetric index, which has the merit that it directly governs a space-time action. And so it's dualizable using string duality to a computation in dual strings. Okay? And because of that, this heterotic quantity appears in Gromov-Witten invariants of these dual Calabi-Yau spaces. And so there's some story involving an interplay between group theory and modular forms and Gromov-Witten theory. Okay, but in any case, we were led after that to think about Calabi-Yau fourfolds. Maybe for F-theory compactification or for whatever other reason. Okay, so the Calabi-Yau fourfold also has an elliptic genus, just like K3. Now it's a Jacobi form of index 2. And that elliptic genus actually has rather interesting structure. It's a linear combination of 2 Jacobi forms of weight 0 and index 2. Here they are. Okay? They're standard generators for the ring of weak Jacobi forms, E4, E6, and some particular functions of Q and Y. And so here I've written that in terms of those. And the coefficients are determined by topological invariance of the fourfold. In particular, the first term here is universal. It's always present. So that piece that's universally present has a really nice expression. It can be written as 1 over 8 to the 12th times a theta function of 2z times a theta function of 0 to the 11th. Now, we're going to see momentarily that this function has a really nice Q expansion and hints at many really interesting things. But in order to remove arbitrariness from my story, guessing about which geometries matter and which don't, I'm going to switch to a setting where all statements can be made totally precise without randomly selecting some particular Calabi-Yau. And you should consider this as a move from the sort of grubby world of these Calabi-Yau fourfolds to a more platonically ideal world. Okay. So here's the platonic realm of 8-dimensional geometry. The most beautiful 8-dimensional space is, of course, the E8 lattice. See, here's the picture. So we're going to begin with the chiral superconformal field theory on the E8 root lattice. The physical theory we care about can be formulated in terms of 8 bosons and their Fermi superpartners, so it has C equals 12. And in keeping with the tradition in Moonshine, we orbifold by a Z2, okay, where x and psi get reversed. The partition function of this theory can be computed by elementary means in terms of theta functions of E8 and so forth. Here's the NS partition function of the chiral theory. Looks like this. You Q expand it. It has a polar term, a 0, 276, 2048, 11202. Okay, and then you can go to one of these websites that lists interesting numbers, and you'll find that, in fact, 2048 can be decomposed many ways by elementary arithmetic, but one of them is interesting, and same with 11202. The natural decompositions are into Conway 1 representations. In fact, it was realized some years ago, starting with FLM and then later, I think greatly improved by Duncan, that this model has a not so manifest Conway symmetry, which actually commutes with the n equals 1 supersymmetry that's present in the sort of orbifold model. Okay. So if you expand this in n equals 1 characters, here's what it looks like. And again, the Conway structure is sort of manifest. This CFT has actually already played a significant role in string theory. For instance, in Witten's attempts to make ADS3 duals of pure supergravity, it's this CFT that was the leading candidate at very low central charge. Now, we've realized several new things about this model, and explaining them will occupy the rest of these 6 minutes that Dave will let me have, 5 minutes, whatever. Okay, so here's the first. It admits an n equals 4 decomposition with more or less manifest M22 moonshine. The elliptic genus and the twining functions that arise match expectations for every conjugacy class, and they all have beautiful interpretations as Rademacher sums. I'll tell you what that is. The natural objects appearing in these genera are Mach modular forms. This gives a completely explicit example of Mach moonshine with a full construction of the module. And there's an analogous story with a different chiral algebra, n equals 2 instead of n equals 4, with M23 replacing M22. In fact, there's a whole family of such stories where you choose the chiral algebra you want. This model is very symmetric. one can, if you want, construct a full string theory instead of a 2D theory that's simply related to this module by considering an asymmetric orbifold that takes two copies of this and acts separately on the left and right. Okay, so if you did that, the elliptic genus would be up to a multiple of the partition function I was just talking about. Okay, so here it is again. This is the partition function of that model. And now we're going to expand it in n equals 4 characters. So here's the expansion. It starts with 21, and then there's a 560, and here's the second line with a 210, an 8470, a 4444. Again, the indices here are conformal weight and spin, and so there's a spin 1 line and a spin 3 halves, 5 halves. So, sorry, so this is 1 half, this is 3 halves, 1, so forth and so forth. Okay. The two lines, the ones with J3 equals a half and J3 equals 1, are actually both governed by Mach modular forms. The coefficients are those of Mach modular forms. And in fact, the dimensions that appear there are those of M22 representations. So the 21 is the simplest permutation representation. The 560 is 280 plus 280, and so forth. Okay, and no virtual representations appear. So what is a Mach modular form? Traditionally, Mach modular forms arise when a theory has to make a choice between modularity and holomorphy. That's not exactly what's happening here, but this is where they've arisen previously in physics. So a typical example is if you compute a supersymmetric index, well, normally massive states cancel on a supersymmetric index. Like the elliptic genus is normally a holomorphic modular object. But if you have a continuous spectrum above some set of discrete states, in the continuum, you may not quite manage to localize on the right moving ground states due to mismatches in densities of bosons and fermions in the supersymmetric theory. And so you can get an object that wants to be holomorphic, but can't really be both holomorphic and modular, and you have to make a choice. Okay. And the result here is that if you want modularity, you have to add a non-holomorphic shadow. And these objects are called Mach modular forms. Now anyway, let me now try to reconnect to the second part of my talk about geometry. There's an equivalent description of the theory I've just been talking about with all these symmetries as a theory of 24 free fermions orbifolded by the action of -1 to the f. That orbifold has manifest spin 24 symmetry because there are 24 free fermions. Choosing an n equals 1 superalgebra gives you Conway zero symmetry. And now to construct an n equals 4 algebra in this description, you'd have to choose 3 of the fermions. These would allow you to construct SU2R symmetries by taking sets of fermion bilinears that give you the SU2 currents. And you can check quickly that doing this construction and acting with the currents on the n equals 1 generates a full n equals 4 algebra. Okay, so I go through the construction here. You get an n equals 4c equals 12 algebra by choosing any such 3-plane in the 24 of Conway. And the subgroup of Conway that commutes with the choice of 3-plane is M22 for some particular choice. There are other groups that you can get by choosing other 3-planes. In this language of free fermions, the elliptic genus should be written this way, as 1 theta function of y squared and 11 other theta functions. This is actually both equivalent to our earlier expression in terms of E8 by non-trivial identities. It's also the thing that appears universally in the elliptic genus of all Calabi-Yau fourfolds, which I think is meaningful, but I won't tell you why in this talk. Okay. Now, the 21 non-n equals 4 fermions, the things that are not part of the SU2 currents, give the 21-dimensional representation of M22, and all higher states in the module have transformation laws that you can just derive from first principles. Okay, so then you can compute twining genera. You can do this in 2 ways. One is because you know all the representation theory explicitly. The other is by the magic of Rademacher sums. Dave is about to end my time, but I'll tell you this really quickly. So in the original monstrous Moonshine, all twining functions were given as help modules. I don't like that word. Help modules of genus 0 subgroups of the modular group. In Mathieu Moonshine, this rule was replaced by something that's equivalent in the monstrous case, which is that the twinings should arise as Rademacher sums with a fixed polar piece. Okay? So here, again, for M22 and M23, all of the twining functions arise as Rademacher sums with a fixed polar piece. And here's my last math object definition slide. What is a Rademacher sum? It's a relative of a Poincare series. You start with the polar piece of a would-be modular form, and then you act with the pieces of SL2Z that don't stabilize in infinity to generate the other terms in the series. Okay, so these are sort of modified versions of Poincare series with better convergence properties. A similar story holds for n equals 2 instead of n equals 4 with M23 symmetry. Again, there's a manifest symmetry. You can twine everything, blah, 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 blah. Okay. Here's my last slide. what is the big picture? We have several examples of mock modular Moonshine with explicit modules. They all arise naturally in the quantum or stringy geometry of certain asymmetric orbifolds. I think there will be connections to geometric models, fourfolds or spin-7 manifolds. They require more work, but I think there's a reason that certain things appear universally in the elliptic genera of fourfolds that also appear here. And there are various promising avenues that we're exploring. Thank you, and I apologize for the speed of the talk.
We have time for a couple of questions.
Do you know if anybody has tried to see in the context of M strings, the elliptic genus, which are Jacobi forms, have any such structure?
So me and my students have played around a little bit with some of the simplest M strings. We haven't found anything. There were papers just today looking at elliptic genera of strings with ALE target. And it seems likely that because you can view K3 in certain limits as being, depending on your duality frame, either collections of ADE singularities or collections of various D5 branes at points in some duality frame, there should be relations between the K3 elliptic genus singularities and M strings. Miranda tomorrow will probably talk about some aspects of that, but I don't think there will be directly a connection to M strings.
Other questions?
The after module correspond to some uniformization map for spheres with functions?
Yes.
You know the specific form? No?
Say again?
You know the specific form of that?
In the case of the monster, or which?
No,
So
in the case you're studying.
in the case that I know, again, these are forms that arise as Rademacher sums. They're not help modules, but yes, one can find the explicit form.
So is there something between m equals to 1 or n equals to 2 where you see something like M24 rising?
Yeah, so between n equals, as I said, you can actually run this story with any chiral algebra you could realize here. So I talked about n equals 4 and n equals 2. N equals 2 in like 30 seconds because Dave is so mean. But between n equals 1 and n equals 2, there's the algebra that's realized on spin-7 manifolds, which is n equals 1 plus a choice of Ising model instead of a U1. And with that algebra, that's roughly speaking going to give you commutants, things that are one planes stabilized by the Conway group. And these things should be able to realize M24, Conway 2, and Conway 3 symmetry. And that's a story we're still trying to work out. But it's almost surely true.
But probably the multiplicities you see look nothing like the elliptic genus or K3.
The M24 module doesn't, I don't think, look like the case of K3, but of course one can also compute elliptic genera of spin-7 manifolds. And there could be a connection with spin-7 geometries. Since K3 is really at C equals 6, and here even with C equals 12, I just barely have room to get M24, I personally am not sure how I'm going to see M24 with C equals 6. But.
It could be K3 squared multiplied 2 or something.
Yeah, okay, fine. You can do all kinds of things with guessing geometries naturally related to K3. Yeah.
Well, let's thank Shamit again. Excuse me.